So up until this point, we've talked about the basic interactions between charged objects and uncharged objects. We know that things with the same type of charge, like positive and positives, repel, negatives and negatives repel. Things with different types of charge attract. Neutral things and neutral things don't attract or repel one another. And we know that all charged objects, positive or negative, attract neutral objects. And so that's kind of the foundation of what we know, and we're going to build on that using this device right here. This is known as a Graaff Generator, and we're going to do some investigations and some explorations using the basic ideas and concepts we've learned from the sticky tape lab to just figure out more about what do we need to know about basic charge interactions. And so a Graaff Generator, it's got a motor in the bottom here, a belt that goes between, and we've got like just a metal sphere right here. And so this metal sphere right now is electrically neutral. And well, you don't take my word for it, let's do the test. And so we've already seen in the sticky tape lab that when we have 3 layers of tape, we take the top 2 layers off, we neutralize it with our upper lip or a piece of metal so it's not attracted to us. And when I separate these things, we know that the top tape acts like a positive charge and the bottom tape acts like a negative charge. And I've actually labeled here just for us to see. So when I separate these things, you can see that they're attracted to one another because one's negative, one's positive. And let's just see what happens when we bring it close to the sphere of our Van de Graaff. So there's our negative charge, it's attracted, and our positive charge is also attracted. So a positive and negative charge would both be attracted to a neutral object. So that kind of confirms that this metal ball or this metal sphere is neutral. So that's nothing interesting yet. So let's turn this on and turn up the speed a little bit. You can see that belt is kind of running up and down. And you should start to hear a little crackle. Okay. If I bring my hand close to the sphere, let's see what happens. Okay. You should be able to see kind of like a little spark there between it and my hand. Okay. What is that spark? Well, that's actually evidence that there are charges jumping through the air, either from it to me or from me to it. We've already talked about the fact that electrons are the mobile charges. Electrons are pretty much the ones that can move, are able to move, are much easier to move between objects. And so when electrons jump through the air, like electrons are so tiny, we can't see them. So that little blue spark, or that shock that you see, we're not seeing electrons because they're so tiny. But when those electrons jump through the air, they're exciting the electrons in the air molecules and the particles of the air itself, you know, jumping them up to a higher energy level, and when they fall back down, they give off light. And so there's a whole explanation for like why we see the light, but all we need to know is when we see that little spark, that's evidence that there is transfer of electrons, either from it to me or from me to it. And so let's so that must mean this has a negative charge, a net negative charge right now, or a net positive charge. Okay, so let me turn this thing off. Okay, and let's see if we can identify what the net charge of this thing is, and then we can explain microscopically why there's the charges jumping through the air. So I'm going to turn this thing back on. And again, I've got some more layers of tape ready for me to go. So I can have a known positive and a known negative charge. So let me make sure this is acting like a neutral charge. Or it's neutrally charged, it's not a significant charge. So I'm going to separate these guys. So now we have something in my right hand is a positive charge, but in my left hand is a negative charge. And you see my left hand is really repelled by that, and the positively charged piece of tape is attracted. So what does it tell us about the charge identity of the Van de Graaff? Well, if the negative is repelled and the positive is attracted, that must mean this metal sphere has a net negative charge. Okay, so the Van de Graaff generator, this metal sphere has a net negative charge. So if I bring my hand close to it, let's think about what's happening. What are electrons jumping from it to me or from me to it? Well, if this has a net negative charge, that means there's now more electrons or negative charges on the sphere than there was when it was neutral. So this belt is actually adding excess electrons to that sphere. And those electrons are negative charges, and negatives, they repel each other, right? So if there's a lot of negative charges all pushing each other away, they're essentially trying to get as far away from each other as possible, just because of the electrostatic force of repulsion, and they're going to jump to some place that's not pushing them away as much. And we're essentially electrically neutral. We've already talked about that before. And so those electrons, and when I bring my hand close, some of them are being pushed away through the air to my hand. So that little shock, or that little charge, or that little light that we see right there is electrons jumping from this to me. Okay. All right, so I'm joined here by my daughter Elise now to see if we can figure some more things out about this based on the fact that we now know this Van de Graaff has a net negative charge.
Yeah.
So if I put my hand close to here, we've already said that there are electrons jumping from the sphere to me. And if I was neutral, and electrons are going to me, let's think about what's happening to my charge. That must mean I've got more electrons on me, negative charges, than I did, so I must have a net negative charge. So let's think about what would happen if I have a net negative charge, if that's true. Getting some by accident. If I have a net negative charge and my daughter Elise is neutral, that means if we do a little fist bump, she should get shocked because the electrons on me, the excess ones, are being repelled to her. So let's just go ahead and find out. Ready? Did you feel anything?
No.
Okay. Which is surprising, right? I just got a whole bunch of electrons. So here's the question. If electrons got to me and there was a whole bunch of extra ones on me, why is it that when I stopped getting electrons in the time that I did to explain things and then did a fist bump, why did she not get shocked? Let's think about it. Well, if I had excess electrons, if she didn't get shocked, that's actually evidence that I don't have those excess electrons anymore. And where could they have gone? Well, it turns out that water molecules in the air can steal some of those excess electrons. And actually, I'm standing on the ground. The ground is neutral, and those excess electrons actually repelled each other and eventually just went to the ground, and it happened in a few seconds. So before we go on in the video, I just wanted to check the claim and test to find out, is the ground actually neutral, electrically neutral? So we have a way to test for that. Remember, we've got our top tape and our bottom tape, our positively charged object and our negatively charged object. And if the ground is neutral, they should both be attracted to the ground. So I've actually spent a little bit of time in my backyard digging a hole, and I'm going to bring it close to the side of the earth and find out, are they both attracted to the earth? So we have our two pieces of tape. I'll bring the positively charged tape close first. You can see that it's attracted to the ground. And let's find out with our negatively charged piece of tape, is it also attracted? Definitely, it's attracted to the ground. And so when something is connected to the ground, in this case it's just a cement floor, but if you're standing on the earth, we'd say that you're grounded. And excess charges will actually distribute to ground. In this case, the electrons will kind of get pushed off. My sphere is standing up a little bit. Those excess charges will get pushed off to ground. And so let's see if I can unground myself and shock Elise when I give her a fist bump. Okay? Well, I'm going to use just some body boards made out of foam, and let's see what effect that has on whether or not, when I'm standing on this, I'm grounded or I'm ungrounded. So I'm going to go ahead and put my hand close to this again. We've already talked about that. There's electrons jumping to me. I should be getting an excess of negative charge. And if that's true, when I stop, I should actually be able to shock. Yeah, now standing up, I should be able to shock Elise. So let's see. Do I keep a net negative charge when I've separated myself from ground?
Yep.
Yep. The answer is yes. The answer is yes. So apparently, these negative charges want to get to something that's neutral, right? Well, when I'm standing on ground, pretty much stay neutral because any charges that jump to me will just redistribute themselves into neutral ground. But as you can see, if I'm separated from ground, in this case by styrofoam, I keep that excess net charge, as evidenced by the fact that when I get electrons, the excess ones stay, and when I get close to somebody who's neutral,
Okay, that really shocked.
those excess charges do transfer, and actually she's grounded like that. All right, now that we understand something about the Van de Graaff, something about being grounded or ungrounded, I want to just kind of think about some of the implications of this a little bit. We said there's net negative charge, there's an excess of electrons here, they want to push each other away, essentially, and they want to get to ground. Well, I guess one question might be, well, why don't they push each other? Why don't they just like travel across this plastic tube and down this metal thing and get to ground? Because all of this is touching ground. So this excess amount of negative charge, like, why does it just stay there? Why doesn't it just like naturally go to ground? They're kind of a buildup on this metal, essentially, and so maybe plastic doesn't allow charges to move like across it or through it. That's possible. So that's actually something I want to investigate, and I'm going to ask for my daughter Elise to join me again to see if we can figure this stuff out. Okay, so while she's coming, we said these want to really get the excess electrons, really want to get to ground. Well, this little connection point right here is actually connected through this little middle plug right there. And if you have like a 3-prong outlet, that middle one right there is connected to ground through wires, like literally through a wire to a stake in the ground. And so when this thing is plugged in, just through the electrical circuitry, and if I plug this into there, this metal ball is connected through wires to ground. So let me turn this thing back on. And if I bring this thing close, you can see that the electrons really get pushed off there enough that they're going to jump to ground. Okay? And so we're going to do a little experiment. Okay?
Yeah.
Elise, we're both ungrounded. You can see that we're standing on
surfboards.
2 body boards, 2 surfboards. So Elise is going to hold the metal part in her left hand. Okay? And I'm going to put my right hand on this thing. If I'm ungrounded, that means I'm getting an excess of negative charges on my body, and they really want to get to ground. Let's see if they can go through us. Okay, so let's do a little fist bump. What do we got?
Went through me.
That definitely went through us. That means electrons float across my skin.
I felt it go like this.
Yeah, across your skin to ground. So that means electrons can flow apparently through metal.
People.
And exactly, electrons can flow through people. So let's find out. Let's find out. Can electrons flow through metal? You want to put that paper down?
Sure.
And I've got an excess of negative charges building up on me. So let's see if we can touch. No, I want you to touch your hand again.
I got tiny shocked. Okay, shocked.
Tiny shock. Let's see if we can build it up a little bit more.
I don't want to get shocked that much.
Oh, it won't be that bad. So I'm getting a net negative charge. At least go ahead and hold on to ground, the metal part, with your left hand. And let's find out, can they go through the metal when you touch it? You get shocked?
I got shocked like 3 times.
Okay, so the charges are able to go through, across our skin, through the metal, all the way to ground. So let's go ahead and try the same thing with paper. Can charges go through paper? So,
what happens if it burns? It lights on fire.
well, let's find out. Okay, so let me put my hand on here. I'm getting a net negative charge because I'm ungrounded. I'm standing on styrofoam.
Okay.
You ready?
Yeah.
Let's try it. So just slowly touch that. Any shock?
No.
Okay. What do you think that tells us?
But it is. It's going towards.
It is because, well, just hold on to it. If you're not getting shocked, does that tell us electrons can go through paper or can't go through paper?
Cannot.
You're right. They absolutely can't go through paper. So we've now just seen evidence that metals and paper, or like plastic or styrofoam, treat charges differently. So we found evidence that electrons can travel across and through metal. They apparently can travel across and through human beings, across our skin. But it doesn't seem like electrons can move across paper. It doesn't seem like they can move across this plastic tube. And apparently, when we're standing on styrofoam, that separates us from ground. They can't easily travel across that. And that basically shows us that there's basically two categories of materials when it deals with how they affect electric charges. There's conductors, where charges can easily move through them wherever they're forced to go. And there's insulators, materials that do not allow the free movement of charges. So we've got human beings and metal are certainly conductors, and plastic, paper, and styrofoam are apparently insulators. They do not allow the free movement of charges across or through them. Okay, one more thing before we're done with this video. We all probably know that when we rub a balloon on our head, it sticks to the wall or kind of can stick to you. It turns out that we can charge a balloon by rubbing it on our hair. So I want to take that idea and use it to see if we can figure out anything more about insulators or balloons for that matter. So before I rub this balloon on my head, I want to know where I rub the balloon on my head. So I'm just going to take a permanent marker and put an X on that balloon, just so we know if we put charge there or took charge away, we're going to find out what happened to it. So we'll let that thing dry a little bit. And I'm going to take this balloon and I'm going to rub it right on that X. And if it becomes charged, that means it's either stripping electrons off my hair, becoming negatively charged, or I'm stripping electrons off the balloon and it's becoming positively charged. So let me remember, I'm neutral, I'm touching ground. If I bring my hand close to it, you can see that where I rub my hair, it's definitely attracted to my neutral hand. So it has a charge. Whether it's a net positive charge or a net negative charge, we don't yet know. So let's take something of known charge identity. In this case, we're not going to use sticky tape. We're just going to use plastic PVC rod, and we're just going to kind of rub wool on it. We've already talked about the fact that this strips electrons off the wood. So this gray pipe has a negative charge. And if I bring it close to this, okay, what is that X doing? Or where I place the charge, notice that it's being repelled by this negative rod. It's turning away from this PVC pipe. Okay, so number one, that tells us that the balloon has a net negative charge, at least at that X location, which means how did it get that net negative charge? That must mean it stripped electrons off of my hair, and so they're now at that X location. Okay, so that's called charging by friction, right? When two different materials are rubbed against one another, it's an opportunity for one of those materials to take electrons from the other if that material has a greater affinity for or a greater attraction for those electrons than the other one. So apparently, this balloon material has a greater affinity for electrons or attraction to electrons than my hair does, and so when we rub the two together, this ended up with more electrons, negatively charged. My hair ended up with less electrons, so it must be positively charged. Well, the last thing we can figure out from this demonstration is this balloon is made out of kind of like rubber, latex, some kind of plasticky material, and it's an insulator. It doesn't allow the free movement of charges. And how do we know that? Well, when I bring this negatively charged plastic pipe close, right, that X is repelled by that, right? It's not the whole balloon that's repelled. It's just the part where I rub my hair against it, which means this doesn't allow the free movement of charges across it, like plastic, like foam, or rubber. But if we do place an excess charge at that location, it stays at that location. So an insulator can have a net charge, as evidenced by the fact that this balloon was attracted to my hand and repelled by this negatively charged pipe, but the charge that it gets, that's forced to be there, it stays there. It doesn't evenly distribute around the insulator. Unlike metal, a conductor allows the free movement of charges, so if you place a charge on it, it's going to spread all the way around that conductor and evenly distribute around it. Okay, now we're going to have a little bit of fun with the Van de Graaff with my daughter Faye. So Faye's going to see if she can try one of the classic things that people do with the Graaff Generator, which is make their hair stand up. And so we'll see if we can do it, then explain why all of that is happening. So Faye, go ahead and step on the styrofoam. And like we've talked about, it's ungrounding her. And Faye, why don't you, I'm going to move this thing over a little bit. Okay? And I want you to put your left hand on there. And I want you to just keep your hand on there. Okay?
Is it going to shock me?
No, because, well, did it shock you now?
No.
No, okay, so it's neutral. There's no charges on here. And so when I turn this thing on, it's going to put charges, but as long as your hand stays there, you're not going to feel shocked. Okay? So I'll go ahead and turn this thing on. And I'm going to explain what's going to happen. I know, you don't feel it shocking you. Because basically, you're not giving the charges enough time to build up here to jump to you, but they're slowly being added to the metal, and they're slowly being added to you, right? So it does feel weird, doesn't it? Yeah. So let me just explain what's happening, Faye. Charges, electrons are going to you, and they're spreading out over your whole body. You are a conductor, and they're spreading out over your hair. And if there are electrons in each piece of your hair that are pushing each other away, that means your hair is going to push all the other hair away from it. And the way that can happen is if your hair stands up. So does your hair feel any different?
Yes.
It definitely looks.
I want to get up.
Can we do a little bit more? You're not going to get shocked. Can you look at the camera? Oh. How does it feel? Weird. Does it hurt weird or just weird?
Yes, it hurts.
Does it? Okay. So what I'm going to do, Faye, is I'm going to turn this thing off. Oh, you're okay. Just take your hand off. Oh. Now, do you want to give me a fist bump?
Oh.
Elbow bump?
No.
Here.
Oh, I don't want to.
Okay.
It's getting shocked.
Maybe a little bit. But
watch your hair go down.
yeah, your hair will go down if we do a little fist bump.
No.
Okay. Thanks for helping.